Hello everyone, True Zero Emissions here. So I was looking at this idea of how can I extract energy from a magnet or from a magnetic field. Excuse me. In one example, this is a magnet here. This is just showing the neutral area between north and south, where the meter is not showing a polarity. It's not showing a north or a south. But this is a plus and a minus, right? So this is the space between a plus and a minus. I wonder if this is what Tom Bearden was talking about when he talked about a dipole, when you have two charges. Because north and south is plus and minus. I don't know which one is plus and which one is minus, but every plus has is surrounded with virtual minuses, and every minus is surrounded with virtual pluses. This is some of the things that Tom Bearden would talk about. I was thinking that I could, for an initial test, some time ago I used an electric motor, and I put my little round magnets on it. I put double-sided sticky tape between the magnet and the outside of the motor, and then I used a zip ties to hold that in place. And I was careful to not spin this too fast. I didn't want to spin it fast enough to throw the magnet off. So I was just doing a very slow RPMs. And for the initial testing, I don't think I need a lot of RPMs. Excuse me. For a more advanced version, I would be interested in having magnets that were in some kind of rotor where the magnets could not come out, right? So I'm going to be looking for something that has that in it. I'm just thinking right now. See, I'm looking at these motors that I have. These are electric lawnmower motors. Very, very powerful. This is an electric lawnmower motor. I like this motor a lot. I like how I think this is what's called an outrunner motor, when the magnets are on the outside. I don't know, but I know the Ryobi, this was in a Ryobi lawnmower, 40 volt, 21 inch, and it had 2 blades. So I'm thinking this has a lot of torque. And Gerard Morin always said that he used to talk about the motors that had the magnets. A larger version of this, like for the old, I think it was for the old a washing machine, had a much larger version of this. But what I was thinking of doing with this one here was my little magnets that I have. Excuse me. Okay, so these magnets, these in here, these magnets. I guess I could use these as well, but these are stronger. And I think I want to use the strongest magnets that I have. So connecting these magnets onto this oops, that's dangerous. Now if that was this magnet hitting that, it probably would have broke the magnet, or it could have smashed my finger. We have to be careful. I have to always be careful, right? So so putting one of these on the motor on each side, just one, having some zip ties hold that in place with double-sided sticky tape. Now, not turning this fast, turning this at a very low speed, right? Because I don't want these magnets coming off of here. I am wearing my safety glasses right now. These are my 3M safety glasses. It should stay on the side there. I noticed that there is a difference in quality. 3M does not make my eyes feel fatigued when I wear them for a long time. So there's somehow a difference, even though it's not easy to see. It does make a difference. And the 3M glasses haven't been giving me any fatigue in my eyes. With the other glasses, my eyes were getting blurry. My vision was getting blurry, and I couldn't figure out why. And someone pointed out that it was the glasses. So I switched over to 3M. I haven't had any trouble since then. So that's what I'm thinking of doing. So one side will have the north facing out, the other side will have the south facing out. And then I was thinking of this motor. So let me see, I'll put the magnet back here, away from the motor. I was thinking of taking this motor and drilling a hole in, oh, here's the motor here. I forgot I put that over there. It's the same motor as this one. So I was thinking of drilling a hole in the wood. Drilling a hole in the wood and then mounting the motor. So placing the hole I drill, placing the shaft in the hole. And that's not to be used. What I'm trying to do is make sure I can screw the motor into the wood, mount the motor, brace it into the wood with 4 screws, right? I could just brace it with 2 screws, like here, like this. I could just have the shaft hanging off the side and just have these 2. Actually, it doesn't even look like that would work. I don't think this is wide enough. I might need to get a wider piece of wood, like a 4x6. I don't know if they make a 4x6. Or just take 2 4x4 side by side and then put the shaft between the 2 pieces of wood and then somehow brace the 2 pieces of wood together. And so this would be like this. And then somehow mount. The thing I'm thinking about right now is, where do I want to place the magnets that are going to be stationary? And that's what I'm thinking about. It's one of the things I'm thinking about is, or that is what I'm thinking about right now, is how do I want to place the magnets that this will be passing, right? So this will have 2 magnets on it, and it's going to be north and south, right? So as it spins, a north pole will pass the magnet and a south pole will pass the magnet. I'm also thinking of using a material, so I'm going to have, where I'm planning to get the energy from is the magnet itself, right? So this is different than an alternator or generator where we have a ferrous metal wrapped with copper wire. Well, what I'm doing here, instead of having a ferrous metal, which is a metal that the magnet will stick to, instead of having a ferrous metal, and I'm trying to replicate, I guess we can call it re-engineering, to use a word that Cameron mentioned to me the other day when I changed something that's already been achieved. Because Donald Lee Smith, created something called the rotating separator coil, which it's right here, Don Smith, rotating separator coil, research and experimentation. And Don Smith did it in a certain way, but what he had was he had a magnet with wire on it, and then imagine the same thing over here with the space in between, right? And he had a north facing this, right? So imagine, instead of this here, imagine a long magnet just like this. This is one magnet, right? North and south, one long magnet, a neodymium magnet, a very strong one. Let's imagine it's like 5 inches long, 1 inch diameter. I think Don was using 2-inch diameter by approximately 4-inch length. That's an approximation. I don't know exactly. At the moment, I don't recall the exact measurements of what he was using, or if that was stated. I think it was stated somewhere, though. And imagine whatever's here, he also had on this side, and the wire would connect to one another. So this side, this wire, instead of going back over here, it would go to the other wire and go through, and then come back and go to something. And Don talks about what he would send that to. I'm trying to recall what he said he sent that into. I don't know if it was a capacitor. I mean, I have a capacitor here, but I was going to go into a full wave bridge rectifier first. I'm not sure if this is AC or DC coming out of here. Someone said by looking at it, it looked like it would be AC that would be coming out of this. So whatever it is, if it's AC, I'll use a full wave bridge rectifier to convert it into DC, and then I would send it to a capacitor or directly into a battery, one or the other, whatever's needed, or whatever's more efficient, whatever charges that battery faster. That's what I would be looking for. I'm not looking for what gets the most power. I would measure how fast the battery charges, right? Because the power going into the battery is not necessarily, it may not be read correctly. You know, it might show 1 amp or nothing, no amps. And it might show some voltage, but if the voltage is going up and the battery voltage is going up and the charge is going up and there's a capacity in there, meaning I can drain that battery, I can run the battery to its full capacity, right? So if it has like 10 amp hours in the battery and it allows me to drain 10 amp hours or whatever is full for that battery, whatever that rating is, then that's what I'm looking at. That's the number I'm looking at. There's debates and arguments and heated debates on how to measure free energy, and one of the challenges that people that measure free energy have faced is that they want to measure how much energy is going into something, and that always cannot be done necessarily, except if you want to measure how much energy is in the battery. And that was the case with John Bedini. John Bedini would charge batteries, but you couldn't necessarily measure how much power was going into the battery because they were high voltage spikes. But every spike has current in it, but our meters are not set up to be measured to measure that, right? Our meters are not set up to measure voltage and current spikes. And John Bedini said if we made a meter, which could be done, it would have to be something that works similar to reading how our brains work. So I know there's a lot of research in brain research, so maybe some of those meters might be able to measure how we're charging the battery. But those are very expensive. I'm imagining they're quite expensive meters. I don't know if those would be used for measuring energy, or if those could be made more inexpensively. Because right now we could buy a regular meter for like $5 and $10. And so I think the brain measuring meters are probably a lot more than that. Brain energy and brain waves and things like that. So, I think anyone on the user side where we're using the battery and we want to keep our scooters charged and keep things going, I think we're all happy to be able to use the energy if it works. But anyone saying, prove it to me, which we already know, all the great masters of energy have said, never try to prove anything. So if you're getting started in free energy and someone tells you to prove it, I'm just letting you know what I was told, and a lot of people say this that are at high levels of free energy research. Never try to prove anything. Just do your research, and if you want to share what you're doing, because I like to share my experience, that's fine. But if I'm on a path of trying to prove something to someone, that's going to be a distraction from what I want to do, because I want to charge my battery and use that energy, right? If I'm trying to prove how that energy is getting in there, that's something that someone has to prove for themselves. That's like, we don't want to do someone else's homework, right? So if someone's asking us to do their work for them, that's something that I've learned to not do. We can just do our own research and experimentation, and allow people to replicate. Hopefully I'm explaining what I'm doing well enough that someone wants to replicate it, they can. So if I'm getting a result that someone wants to replicate, hopefully they can do that. Right now we're just looking at theories and drawings, so I have to see where this is going to go and if it does anything or what it can do and what it does do. And I have to be open to looking at things that might be there that may not be what I was looking for. That's another thing that is really big with people that are at high levels of free energy research. And again, free energy research, it's not free, it just means highly efficient, right? That's my understanding of what we're talking about. We just use those words because they're what we understand to be as extreme efficiency in terms of extreme efficiency systems. So I'm thinking of so Don Smith's rotating separator coil where he had a magnet here and a magnet over here, and then he was interrupting the flux between the two sets of magnets. He was fluxing them. I don't know if we call it fluxing or interrupting the flux. When we interrupt the field where the magnet, when the magnets are close together like this, let's say this is a long magnet, right? if my finger's a magnet and it's here, and if I pull my finger away from this, let's say the tip of my finger is a north, and I'm pulling it away, I can go to a certain distance where where a meter, right, a meter that reads north and south, will read this as neutral. It won't read it as two separate magnets, right? Because the moment it becomes two separate magnets, we're going to have a south on that side and a north on this side, right? As we're moving the distance away. Or as we interrupt the field with something, bring something between there. So it's the difference between putting something between the magnets and moving that away, and putting it there and moving it away, something that can interrupt that field. And the way we know it's working is this will become a south and this side will become a north. And then when it's blocked, or then when it's allowed, when we remove the shield, if I call it a shield, when we remove it, the shielding, then it becomes a neutral again. It's not north or south. So if I just move my hand, if my hand was a shielding material, right? Don said we can use, there's many materials he mentioned, but one of them was neodymium magnet dust, and use some kind of adhesive to glue it onto something, a material. But I also wonder if copper could be used. I think a magnet can be used too. That would take more energy. It wouldn't be as efficient, I think, because the magnet's going to want to stay there. But I think a magnet going between here can also cause this to switch as well. But I don't know if we'd want north facing this way. Let me look at this for a second. How would we want that to be? If my hand was a magnet, would I want north to be facing that south and the south to be facing the north? Because then it's going to want to pull, each side will want to pull the magnet toward it. Or would it be the other way, where it's south facing south and north facing north, and then go in between the two? I guess I could just try both ways and see what happens, see what comes out of the coils, right? So this side of the coil would still go there, but this side would go to this coil around this magnet and then go back to here. This is a full wave bridge rectifier, and then going into a capacitor and then into a battery. Just see what it does. That's just my own thoughts on that. Don has in the book Magnetic Resonance Energy Crafting Systematic Index by Richard Friedrich, which is the collected life's works of Donald Lee Smith. And Rick brought it all together. It's really great. It has emails in there, Don talking to people about how to do things and what not to do and what to do and how he understands things. And my understanding was that Don was teaching all that he could without saying too much about, because he had a lot of business agreements, and Don has inventions all over the world that are being used that someday will be just available everywhere, but the idea is that it's a very slow transition. What speeds that transition, I think, is just people experimenting at home and experimenting in their garage, in their basements, and moving the theory, progressing the theory forward, moving it forward. That was Don's dream. Don's dream was that we could all have access to this technology. And I think the more public that has this technology is when the businesses will start to bring out the technologies that they have, right? Which there's no limit to that. I mean, everything that we've seen in science fiction in terms of, I'm not talking about weapons, I'm talking about, because we have to stop fighting, we all know that, right? We can't have both sides making more deadly weapons and more destructive weapons. We have to stop fighting. So there's no excuses for fighting, there's no reasons to fight, and there's every reason to collaborate and every reason to stop fighting. So we know we can't do that. But using technology as a tool to offset the pollution that we're causing to the environment, to the air, to the water. And this is everyone's dream. Everyone wants clean energy. Everyone wants clean air. And anyone that doesn't believe it's possible, but doesn't have time to study all of the research of Richard Feynman and John Wheeler, Princeton and Caltech, right? or hasn't heard of the quotes, there's enough energy in a teacup. In the space of an empty teacup, there's enough energy to power the world endlessly, right? Because space, as soon as we use the energy in space, it replenishes itself instantaneously. I think the rate at which space charges, which space charge is available is 10 to the 120th times per second. So that's a 1 with 120 zeros behind it. That's how fast space is fully recharged, right? So our cycle right now, we're running out of the wall 60 cycles per second in a sine wave, right? And Tom Bearden shared his life's research, which was researching other great masters of energy and understanding of others that have understood and studied energy throughout their life. I mean, we're talking about standing on the shoulders of giants, standing on the shoulder of giants, standing over the shoulder of giants, like over and over and over, right? Tom Bearden was standing on the shoulder of giants. We're standing on his shoulders. It just goes on and on and on. So Tom Bearden researched thoroughly and extensively and documented and collected works and thoughts of just great achievements in understanding. And Tom Bearden has many books out that are available. I'm thinking they're on Amazon and probably eBay as well. And I think a lot of the research is available on the internet as well. So what I'm thinking is, how many different ways can I... And right now I'm kind of focused on this neutral area, which is often called the BLOCH. And I put watts there, right? Because we want to get watts out of here, right? And Don often said that it's so easy to get energy from a magnet. It's so easy to get energy from a magnet. He kept saying that. And everyone says that achieves efficient energy extraction from magnets. Every single person says the same thing. They say, things like it's embarrassingly easy, it's easy. But this can be said of anything that's complex and once understood is then like, wow, I can't believe how simple this is. I mean, I think everyone says that about everything, right? Or almost everything, many things, most things. But if we look right now at the way motors and generators work, like this is a motor that can be used as a generator, right? So if you put energy in it, it's a motor. But if we spin it and put a load on it, right, then it's a generator. So if I connect this this has 3 wires that are coming out of this, and if I cut the wires and I separated the wires away from one another, because right now they're really close together, it would be hard to connect to the wires with the way they are there. But I could cut the wire, strip the insulation off the wire, and then connect 3 different wires to a full wave bridge rectifier, which has 3 wires going in and then a plus and a minus coming out. And then if I put a load on that, like I connect that output from the full wave bridge rectifier to a light bulb or a battery, and then I spun this. Like right now this spins very easily, right? Right now this spins very easily. I have different motors and some are really hard to spin. Like the magnets are so strong. This one happens to be very easy to spin and has a lot of torque, right? That's very interesting. And look at all that copper wire this one has. This has a lot of copper wire. So my understanding is those copper wires are wound, and that's a pretty thick wire right there. I don't know what gauge that is, but it is a thick wire. Is that damaged right there? It almost looks like it's... No, that's just the outer coating. So so this is a ferrous metal now they're right here on this. So I'm going to call this a generator because that's what we're going to... Well, we're going to use this as a motor, but this can also be used as a generator. But I'm going to refer to this as the generator for the moment. So this generator, using this as a generator, we have the magnets on one side, right? And that's where all the energy is. The energy is where the magnets are. But we have the copper coils wound around the ferrous metal, which is the metal that can be magnetized, right? So as the magnet passes this passes this iron. Excuse me, I'm gonna have to drink some water. As the magnet passes by this metal, the metal becomes polarized, so it becomes a north and a south, because these are north south, right? That's how the magnets are. So each of these metal arms coming out, right, are that are wrapped with copper wire, are switching from positive to north to south, north to south, north to south, and that makes a voltage in the wires, right? And the thicker wire gives us more current, and the thinner wire gives us more voltage. That's my understanding. These are beginner thoughts that I'm sharing with you, so apologies if you heard this before, and apologies if I'm wrong. I don't think I'm wrong, though. This is my research and study indicate what I'm saying, but I am clarifying that I'm a beginner. So, my understanding, comparing this to Don Smith, Don says, let's get the energy directly from the magnet. Let's wrap, instead of wrapping metal that is not even a magnet, but becomes magnetized, becomes north, south, switching between the two, right? But still, only for that brief moment. I'm going to get some water. Give me a second. Okay, I got some water here. Apologies for the interruption. So instead of switching between the switching the metal between the north and the south, and north and the south, and north and the south, the same one, right? And all these are doing that. All of these are doing that. Instead of switching it back and forth, and one question might be, what if all the magnets were north, facing north inward? What would it do then? That's an interesting question. I think Gerard Morin, I don't know the context of what he was saying this in. I don't know if he was talking about it being a motor or a generator, but he said that when he made everything north, instead of north, south on the magnets, it did the same thing. It still worked the same. But I don't recall at the moment if he was using it as a generator or as a motor at the time. And I'm thinking probably using it as a generator, because that's what he often was using, is these generators to what he called pump energy from the environment into the circuit, which does make logical sense to me. It makes sense that it's doing that, because we don't make energy, right? When I read, how does energy come from copper coils? How do we generate energy? All I hear when I read anything I read, I'm just hearing them say that we're making energy. We were already taught that we can't make energy, so why would we say that we can make energy just because it's worded in a way that doesn't sound like we're making it, right? Like perturbing the electrons or something. I don't know what it says, but it's saying we're making energy. So can we make energy or not? Which one is it? So that's a rhetorical question. I don't need an answer to it. All I need to do is keep doing my experiments. So we see the distance between the magnets and the metal, the ferrous metal, which is a metal that becomes polarized by a magnet once the magnet comes close proximity to it, is very close to the magnets there. It's very close, right? So what if we take the coils, the copper coils, and wrap the copper around the actual magnet itself, right? I don't know what's going on with my voice. It's really annoying, though. It's like I'm not thirsty and I don't want to drink water, but my voice is very dry. Be right back. Okay, so apologies for the interruption. So yes, instead of wrapping the copper coils around a metal that is not a magnet but can be magnetized, right? Just wrapping the copper wire around the actual magnet and then shifting the magnetic field, shifting it, right? Fluxing it, fluxing the magnetic field by bringing another magnet in close proximity to it. And how many different ways can we do that? Because another idea I had, because I'm trying to think of all the ideas I can, and I'd like to build all of them at the same time and see if one of them works, or if they all work. One idea I was thinking about was if I had two, we'll just say, I guess we could say electric motors or something. And then this comes out. This comes out. Now, what are these? What do you think these are that are coming out here? What's your guess? Okay, excuse me a moment while I do this. What would you guess these are? So in our motor generator that we just saw, I was calling these arms, right? And they might have a different word. They might be called legs or something, I don't know. Apologies that I'm clearing my throat so much, but I have to, because to talk I have to have my throat clear. Now I'm just going to draw these here, but they're not going to, the number's probably not going to match. But let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, 11, but they're not proportional. They would have to be exactly equal, right? All the length, everything. Now, what do you think these are? So before we saw these were a ferrous metal, right? Which is a metal that when a magnet touches it, first of all, a magnet will stick to it. And when it does that, that metal would become magnetized for that moment. And as soon as the magnet is pulled away from it, then it's not magnetic anymore, right? So what we have here, let me try to see how I would do this. I'm not sure what the most efficient way to wire this would be, but right now I'm just going to say that these will all be in series. Okay? And this is going to be very messy, but I'm just to get the idea, okay? We would have the same windings that we just saw in the motor generator that I was looking at. Or more. Maybe these are even larger than those. Okay, and then so the wire would come out, or it would go, let's say, here, and the other end would go here, okay? So that's the two ends of the wire that goes around this whole thing. And these are all in series, we call it, right? And then we have the same thing on this side. So I don't know which way I would wind it. I would have to think about that, if it'd be the same way or the opposite way. But for now, we're just going to do the same thing. Because there's so many different tests and experiments that could be done, right, to maximize efficiency. I mean, those students that made the R Walker self-charging electric scooter, I think they took a year researching with their teachers, and they made a self-charging electric scooter. Isn't that great? And it charges itself. Once the generator reaches 2,000 RPMs, it's self-sustaining. And it just had one battery. And in the video, if you watch the video, and I think it's on overunity.com's page, but if you look up R-Walker, so R-WALKER, I guess you could just say like self-charging free energy scooter. I don't remember what the proper title of it is, but I know that name's correct, R. Walker. But by putting self-charging free energy scooter might pull it up. But I don't think they did this, but I wonder what they did. I wonder if they're using something, a variation of Don Smith's rotating separator coil, right? Okay, so in this instance, what do you think we're going to do? So these can spin. These can spin. So if this spins, this would spin, right? These are magnets, by the way. Each of these are magnets. So in this case, I might have all of these north facing out and all of these south facing out. That way, as I turn one of these, this next one would catch that, this next one would catch that one, the next one would catch that one. So I'd spin this really fast. And what's happening here? I think what's happening is here's the reason. What I don't like about this is that the area of the magnet is so small. Look, see how small it is? How do I maximize the area that I'm extracting energy from at any given time? So I already don't like this design because the power is only coming from this area and not from any of these. I want it to come from all of these at the same time, right? So this has a greater surface area of energy at a given time, at any given time. I think we're using the whole entire magnet here because this whole magnet is fluxing as we move a north and then a south and a north and a south against this. And I think this could also be placed on this side as well and what would be most efficient? Would it be if there was a way to have these so that they're doing the same thing at the same time? Let's see. So this one has, yes, so this one would be in a, let's see. Well, we'd have to try it both ways. In one test, when this north is at this south, right, because this rotates, this stays still, right? This one's staying still. It's staying in one place. This magnet just stays there. This spins, right? It's spinning. And when this north comes across the south right there, maybe on this side, I would have, so let's see, I think this north being here pulls the neutral area this way. It fluxes it this way. So I want to help that flux that way. So I think I would put a north here at the same time as the north is here. And that would help shift this over. It would help push the flux this way. But I could also do the same thing that this is doing. Oh yeah, I already said that. That was the same thing. That was the same thing. North here and then north here. Yeah, I would try it that way. And I would also try when north is here, a south is here, rotating, right? But these would have to be on some kind of gear that made sure those were always synchronized exactly the same. But also it would be interesting just to spin this freely, just freely spin it, and then freely spin another one on this side that was also north-south, and just see what it did, see what this did, right? Even just the randomness at randomly pulsing this thing at random times, because at that point it's completely random. So some spikes, there might be some high voltage spikes and low voltage spikes, and the current would be fluctuating, and it wouldn't be constant, I don't think, for sure. But or if I want more constant, I would just use the one that would be a very consistent. You know, how many pulses do I have, right, per second? So 33.3333 all the way down, as far as we can go, I think, is what? the R Walker that we just were talking about, the R Walker, self, sustainability, transportation, cost approximately $200 to make. They made it from used parts. Now think about this. That includes the motor. The generator, I mean. Yeah, the motor too. But the generator that's charging that battery, they used used parts to make it. They didn't invent anything new. It's like cooking. I've been told many times that oftentimes we're getting the same food, but just in different combinations or prepared differently, right? These students collaborating with their teachers, which is a wonderful thing to do. My only recommendation for improvement would be to share the foundational theories and principles of your invention. You don't have to share your exact invention. And this is to students all throughout the world. But the public must understand. It must have access, simple access, meaning just make lots of videos of the foundational principles and theories of what makes your system work. It doesn't have to show your specific invention, right? But it needs to show the theories of how the energy is flowing from the 0-point field, which that's where all energy comes from, into your circuits, right? Into your system. Because otherwise we just have all these shelves with amazing inventions sitting on them, and that are slowly coming out over time, very slowly, right? But what we need right now, there's an urgent need for understanding extremely efficient energy systems so that we can help contribute to the solution of having cleaner air and low-cost energy and clean energy, not energy that's the byproduct is very dirty, right? We don't want that. Like nuclear energy, if we have nuclear waste and it's getting buried and all these things, I don't know what's happening with it. I haven't kept up on the latest of that, but I just know there's so much nuclear waste in the oceans that was dumped all over the oceans, hundreds of thousands of barrels of nuclear waste. And I don't know if that's ever been cleaned up. I've never heard of anything about that being cleaned up, but there's just drums leaking in the ocean. A book I was reading was saying that hundreds of thousands of drums of nuclear waste was dumped all over around many islands deep in the ocean, right? And so imagine that. Imagine being at an island, you think it's so beautiful there, and there's nuclear waste in the water. That's terrible. I will have to find out what book that was and then share that book with you and share what page that was and everything, so you'll have a reference for that. I read many books. So on this R Walker scooter, which can be found on overunity.com's, I think that's the name of his YouTube channel. He has that video shared on there where he's talking about this, and then also runs the television. He runs the actual footage of where a news team interviewed the students and talked with the young students. One of the students was 17 years old, and the two students were at the school working with teachers and collaborated on this self-charging electric scooter, and achieved at 2,000 RPMs, which means turning 2,000 times. So once is like this: 1, 2, 3, right? How many times does it turn in 60 seconds? So I said 2,000 divided by 60 to find out how many times it turns. I think that's the right way to do it. If I'm wrong, please correct me and make a video of it if you want to. But I divided 60 into 2,000 to get 33.33333, which means it turns 33 times every second. 33 times in 1 second is how many times that generator turns. So that's a lot of activity. So if they are using some version of a Don Smith rotating separator coil where they're using the flux, right, when they're fluxing something inside that little generator, which is the size of my fist, right, it's like this size. It's like that long, right, which is like maybe 3 or 4 inches long. It looked like it was, the diameter was maybe 2.5 or 3 inches. And that's it. It wasn't big. Inside that, which they open it up and they somehow change things inside there. What did they do inside there? That's what I'm wondering. I think that there's magnets in there. I think there's copper in there. And because I know, my research and study indicated strongly, and without any doubt at all, that voltage spikes, a voltage spike has current in it. And that current is delivered before the voltage. This is not something we can measure, but the battery will fill up. If we use high voltage spikes, we can charge a battery with that. But never overcharge the battery. When the voltage is full, that's it, it's done. And if the battery gets hot, stop. And then if you do any of this, it's at your own risk. I'm not saying anyone should do this. I'm just doing this because I enjoy experimenting. So, but voltage spikes will charge a battery, even a lead acid battery, a large battery, right? So, at 2,000 RPMs, they have a small battery on the scooter. The scooter's not a racing scooter. I don't remember how fast it goes. I think I looked it up a long time ago when I calculated it, because they were talking about, I think, kilometers per hour, and it's been years now since I calculated it. But I think that scooter was able to go, I think it was able to go like over 20 miles per hour, possibly 37 miles per hour, if I recall correctly, but confirm this for yourself. But this scooter could charge itself once it reached 2,000 RPMs, once the generator reached 2,000 RPMs. Now, again, that can be done with gearing. So if we don't want to go, to get the generator to turn 2,000 RPMs, if it requires going a speed of 20 miles per hour, but we want it to be able to stay charged at 10 miles per hour, that could be done with gearing, right? With the gearing. So these are what I'll call low resistance charging systems, because I'm calling it that now as a thought experiment. I don't actually know that it is. I think it is, because if there's a load here on these wires, does this become harder to spin past this south? Does the north and south harder to push past that? Because if it's not, then I think we can call this a low resistance battery charging system. Because I know that if this was copper, right, if this was copper, which is the way that generator's made, right, and this is coppered, we'll call this one of the arms, right, of all the arms that stick up inside there that we were looking at earlier. Well, when we put a load on that to light a light bulb, to charge a battery, then I think this becomes harder to pass the magnet past this. It's like the magnet slows down going past this. But if this is a magnet, now, yes. Isn't that interesting? I just love this. I'm sorry, I feel like apologizing for getting overly excited in so many of my videos. I should stay calm, right? People say, be calm, be calm. I don't know, I like being excited. I just like showing my enthusiasm for this. I mean, there's words, some of my favorite words are like these ideas of like boundless enthusiasm and inspiration and all these things. I just love those words and what they mean. And that's how I feel. I just am excited to learn and to share what I learn. I mean, what's the point of learning something if I'm going to keep it a secret? Now, some people that are famous sometimes will say that because they're famous, they can't share everything. So it seems like it's important to not become famous. So if you just want to be a nobody, right? And just do your experiments at home and learn things and share things, and then make your scooter charge itself, and other people can replicate what you're doing, then I guess everything's okay, because we're allowed to pursue happiness. But it also seems like people that are even famous, I don't know what famous means, but if someone thinks they're famous, that they still should be able to share what they think. But I guess we can make up stories in our minds that put limits on our actions, right? Where we can limit ourselves because we believe what someone says, or someone tells us what we can do, and we think that's all we can do. But, it just seems like we have the freedom to create, and we must create. How can we not? We are created. That which is created must create, right? And we are created, and we must create. So anyway, this is a thought, and this is another long video, but I'm happy to make this and share my thoughts with you. And I don't know what the next step is. Because I'm thinking, like, how do I place the magnets on the wood, and how do I do this? But you know what? Thomas Edison, I think it took 1,000 tries, 1,000 attempts before he got the first light bulb to actually light up or to work for any length of time that was considered successful to him. So if it takes me several thousand, if it takes me 1,000 times of trying this in different ways, moving the magnets, moving the wire, trying different magnets, trying different configurations of where I place the magnets in relation to the magnet, where I place these magnets around this, 1,000 different ways, different wire, different everything, different thicknesses. What if I use welding wire around this, wrap thick welding wire around this, right? I have some of that over there. I saved some of that. I have some over there, right there. You can see it, the red. See that red wire? I don't know if you can see that, but that's welding wire right there. And I collect things from my experiments, and then I have them when needed. And I don't think I could say one word until I've done 1,000 experiments on this alone. I can't say a word, not even a word. I cannot say, it's not working, darn. I can't say that. When I get to 1,001, then I can say, this isn't working. I feel frustrated. But Thomas Edison, at the end of his life, right, the last days, he said, when someone asked him, how does he feel about his work, his life's work? He said, I'm just getting started. I'm just getting started. Okay, everyone, until next time. See you soon.